Welcome to the deep dive. Today, we're looking at something, well, literally foundational, how buildings react when the earth shakes. How do engineers make sure our structures stay standing during an earthquake? It really boils down to understanding how a building naturally wants to sway. It's sort of seismic signature. And for this deep dive, we're going to unpack a really fascinating new study, Sharaf et al., 2025. They've come up with a fresh way to predict this fundamental time period for reinforced concrete buildings. And this isn't just engineering jargon. It's critical for safer cities, smarter construction, really vital stuff.
Absolutely vital. This fundamental period is genuinely one of those critical numbers in our building codes pretty much everywhere.
Yeah.
It dictates the seismic forces engineers have to design for.
Right.
So getting it right is paramount for safety, obviously, but also for making sure we're not overspending on the design. Efficiency matters, too.
Okay, so let's nail this down first. This fundamental period of vibration, what does that actually mean? If I'm picturing a building, what is this natural rhythm?
Yeah, think of it like a really big, slow pendulum,
Oh,
or maybe like a tuning fork. Every single building, whether it's your house or a huge skyscraper, it has a natural way it wants to sway back and forth if you nudge it.
okay.
The time it takes for one full sway back and forth, that's its fundamental period. Each building has its own unique rhythm.
And I guess that rhythm is super important for earthquake design because, well, if the building's sway happens to sync up with the earthquake shaking.
That's exactly the danger zone. It's called resonance.
Yeah.
Like pushing someone on a swing, you push at just the right moment, they go higher and higher.
All right.
An earthquake can do that to a building. So engineers use this period to calculate the forces the building needs to handle, the design-based shear and lateral loads. The aim is always to make sure the building's rhythm doesn't match the likely earthquake shaking.
And if those first calculations are wrong, that has big consequences, doesn't it? Not just safety, but cost, too. The study mentioned that underestimating this period, maybe even trying to be conservative, led to overstrengthened and uneconomical designs.
Precisely. You end up building something much stronger, much bulkier, and therefore much more expensive than it realistically needs to be. All because that initial period calculation was off.
So where did these calculations, these formulas come from originally? Building codes like the UBC, the ASCE standards, they've relied on empirical formulas for ages, right? How did those come about?
Well, yeah, for decades. Many of those formulas came straight from looking at how real buildings behaved in past earthquakes.
Yeah.
Data from events like the 1971 San Fernando quake in California, that was hugely influential.
Yep.
These formulas usually just looked at really basic things, like the building's total height, h, or maybe the number of stories, n. You'd see equations like T equals C subscript T times H to the power of 0.9. Simple relationships based on observation.
Practical for the time, I suppose.
Given the data they had, yes.
So these early formulas were a starting point, based on what we could observe. But clearly they weren't perfect, especially as buildings got more complex. What were the big problems that started showing up? What pushed researchers to look for something better?
Oh, the limitations became pretty obvious over time. Studies back in the mid-90s, for instance, show that these code equations often seriously underestimated the actual measured periods.
Seriously underestimated? By how much?
Sometimes by a huge amount. Like, the real period could be double what the formula predicted, maybe even more in some cases.
Wow.
And that directly leads to those overly conservative designs we talked about. Designing for forces way higher than necessary, costing a lot more. A big part of the problem was that they were just empirical, based on, frankly, pretty small data sets sometimes. And they often ignored really important physical factors, the actual mass, how stiffness was distributed, weird building shapes, things that really affect how a structure moves.
So they were too simple, basically.
In many ways, yes. For example, the ASCE 705 formula, widely used, it was found to really underestimate periods for tall buildings, like maybe a 45% error for a 90-meter building compared to detailed computer models.
That's a huge difference.
It is. And the UBC formula wasn't reliable for taller buildings either, over about 40 meters. Even attempts to update them, like Salama's equation in 2015, still generally predicted periods that were too short, likely because they weren't quite capturing the building's flexibility, especially, say, how concrete cracks might affect stiffness.
Okay, so the old methods had real limits. Understandable, then, that researchers started looking towards, well, more powerful tools, more data, more computing power.
Exactly. And that's where machine learning, ML, started to come into the picture for period prediction. There's been some really interesting work.
Like what?
Well, Kumar and colleagues in 2025 found artificial neural networks, ANNs, were better at predicting periods for buildings with irregular shapes. Raman et al. Used interpretable ML using things like SHAP values.
SHAP values, what are those?
Sorry. It's basically a technique that helps you understand why the machine learning model made a specific prediction. It shows you which input factors were most important. So they use that to figure out key parameters in skilled buildings.
Okay, so trying to make the AI less of a black box.
Precisely. And others, like Shan et al., even used ML to look at existing buildings, considering how materials might degrade over time. So lots of activity in the ML space.
That sounds really powerful. So if ML can do all this, why isn't it just the standard approach now? Why aren't engineers using it for every single design?
That's a really good question, and it hits on the practical challenges. First off, these ML models, they need a lot of high-quality data to learn from. And, you don't always have that perfect data set for every possible building type or situation.
Right, data can be hard to come by.
And second, they can be computationally heavy. You need powerful computers and, frankly, specialized skills to build and run them effectively. But the biggest hurdle, often, is that black box problem you mentioned.
Yeah, the interpretability.
Exactly. Unless you use specific techniques like those SAP values, it can be really hard for an engineer to understand why the model is giving a certain period. And if you can't understand the reasoning, it's tough to fully trust it, especially when safety is on the line.
That makes perfect sense. You need to trust the tools you're using for something this critical.
You absolutely do. Relying on a number you can't explain is, well, it's not ideal engineering practice.
Which neatly brings us back to the core of this deep dive, this new analytical approach from Sharaf et al. They were looking for something more logical, more physics-based, right? Something that avoids the simplicity pitfalls of the old formulas and the black box issue of pure ML.
Exactly that. They wanted a model that made physical sense.
And their big idea, as I understand it, was to simplify the building down to a single degree of freedom system, an SDOF. Talk us through that. How does picturing a whole building as just one weight on one spring help?
It sounds almost too simple, doesn't it? But the elegance is in how they make that simplification work. So instead of modeling every beam, column, floor plate, which gets incredibly complex, you represent the whole building as an equivalent mass, mech, sitting on an equivalent spring, kek.
Okay.
And the period of that simple system, it's a classic physics equation, T, 2 times the square root of mech divided by kek. The real breakthrough from Sharaf et al. Is how they figured out ways to calculate those equivalent mass and stiffness values easily and accurately from the building's basic properties.
Okay. So the SDOF idea isn't new, but calculating those equivalent values accurately and simply is the key innovation here. How did they do that? What were the clever steps?
This is where it gets really interesting. For the equivalent stiffness camp-like, they found something quite remarkable. They discovered that for typical concrete frames, it's mainly the stiffness of the first 2 stories that governs the overall lateral stiffness of the entire building.
Really? It's just the first 2 floors.
Mostly, yes. It's a dominant effect. And knowing that allowed them to come up with a much, much simpler way to calculate kick. It bypasses a lot of the complexity you'd normally expect.
Wow. Okay. And what about the mass, the mech?
For the equivalent mass, instead of complex calculations, they developed what they call an equivalent curve. It basically lets you find meek in a single step, just based on the number of stories in the building.
Nice and simple.
Very practical. And they also accounted for buildings where the columns and beams aren't the same size all the way up non-uniform sections. They developed a correction factor based on the ratio of beam stiffness to column stiffness. They call it the alpha ratio. So it's adaptable too.
That sounds incredibly practical. Simplify the problem, find clever ways to calculate the key inputs based on dominant effects and simple parameters. So what does this mean for engineers on the ground?
It means they get closed form expressions, clear, direct equations. You can see exactly what parameters are influencing the period height, mass, stiffness contributions. It's inherently interpretable.
No black box.
No black box. You don't need super complex software or massive data sets for a reliable preliminary estimate. It strikes a really good balance, accuracy, ease of use, and you can actually understand why you're getting the number you're getting. Transparency.
That sounds like a huge step forward. But the proof is in the pudding, as they say. How well does it actually work? How did they test it?
They tested it rigorously. They compared its predictions against results from high-fidelity finite element method analysis, FEM. That's basically the gold standard computational model.
Yeah, and the results.
Pretty impressive. For standard uniform buildings like 6 or 10 stories, the error compared to FEM was tiny, like 3 or 4%.
Wow.
And even for the non-uniform buildings, using that alpha correction factor, the errors dropped to as low as 1% in some cases.
Mm.
Really accurate. And when they compared it head-to-head with the older code formulas and other empirical equations, their new equation consistently came out on top. Much better prediction accuracy, lower errors, higher correlation.
Can you give an example?
Sure. In one comparison test, their equation had an R-squared value. That's a measure of correlation of like 0.998, almost perfect, with a tiny error. A well-known older formula, Goel and Chopra's, applied to the same buildings. It had an R-squared of just 0.14 and a massive error.
Okay, that's not even close. Huge difference in reliability.
A massive difference. It really highlights how much better this new physics-based approach performs compared to some of the older empirical fits.
So it's accurate overall, but let's dig into why. What specific building characteristics matter most for the period, and does this new model capture those dependencies well? They did that sensitivity analysis on 125 different building models, right?
They did, yes, and it gave some very clear answers. Unsurprisingly, building height is the biggest factor. Taller buildings sway more slowly longer periods. The new model tracked this relationship incredibly closely with FEM, near-perfect R-squared values. Older formulas often struggled, especially with taller structures.
Okay, height is number one. What else?
Seismic mass was the second most important. More mass means a longer period, more inertia. Again, the proposed equation captured this really well, high correlation. The existing models, they were much less sensitive to changes in mass, which isn't right physically.
Interesting.
Then there's span length, the distance between columns. Longer spans generally mean a more flexible building, so a longer period. The new model predicted this correctly. The other formulas, they actually got it wrong. They showed negative correlations, meaning their predictions went in the completely opposite direction to the FEM results as span changed.
That's not good for the old formula.
Not good at all. It shows they're missing some fundamental behavior. And finally, things related to stiffness, like that beam-to-column ratio, alpha, and the material stiffness, E. While these have smaller effects in typical concrete buildings, the new models still capture their influence accurately. The older models often showed statistical deterioration, basically. Their predictions fell apart when looking at these subtler effects.
So wrapping up the validation, the new model isn't just accurate on average. It accurately reflects how the period changes when you change key building properties like height, mass, span, and stiffness.
Precisely. The average ratio of the FEM period to the proposed period was almost exactly 1.00.
Yeah.
Very little bias. And the variation was tiny, like a 2% coefficient of variation. It's consistent and unbiased.
That's really convincing, but no model is perfect, right? There must be limitations or situations where this new approach might not apply as well.
Absolutely, and it's crucial to understand those. Firstly, this model was developed and tested mainly for regular buildings with fairly uniform layouts, where mass and stiffness are evenly spread out.
So complex shapes might be an issue.
Potentially. Its accuracy for irregular buildings, ones with big setbacks, weird corners, or where twisting might be significant, hasn't been fully validated yet. It might need recalibration for those cases. Secondly, all the validation assumed the building was fixed rigidly to the ground, a fixed base assumption. It doesn't account for soil structure interaction, or SSI.
Ah, right. If the ground itself is soft and moves with the building.
Exactly. That can significantly change the building's effective period, especially on soft soil sites. That interaction isn't in this current model. And third, it assumes the materials behave in a linear elastic way. Meaning it doesn't fully capture complex things like concrete cracking or steel yielding, where the stiffness of the materials changes significantly under strong shaking. That's non-linear behavior, which this model doesn't directly address.
Okay, so regular buildings, fixed base, linear behavior, those are important boundaries to keep in mind. And areas for future research, I imagine.
Definitely. The paper acknowledges these are areas for future work, incorporating things like the number of bays, maybe explicitly adding SSI effects, tackling nonlinearity. There's always more to refine.
So let's bring it all together. What's the big picture takeaway here? We've dived deep into building periods, old formulas, ML, and this new analytical approach. What does it mean for designing safer, better buildings?
It means we're moving towards more robust, more efficient ways to do that crucial preliminary seismic assessment. Engineers get a tool that is accurate, physically intuitive, and transparent.
No black boxes, easy to use, reliable.
Exactly. And that ultimately helps in designing buildings that are both safer for the people inside and potentially more economical to build. It's about enhancing resilience in our cities through smarter engineering.
It's fascinating how understanding something seemingly simple, like a building's natural sway, its fundamental period, is so critical. It really is like predicting its dance with these invisible seismic forces. And maybe that prompts a final thought for you listening. Think about other complex systems around us, maybe bridges, maybe financial markets, maybe even our own health or habits. What are the unseen forces, the natural rhythms or responses at play there? And how could a deeper, more accurate understanding of those fundamental periods lead to more stable, more predictable, maybe even better outcomes? Something to ponder.